to our First Flight kickoff streams. My name is Jess, and today we are going to be doing a walkthrough of the latest First Flight competition that has launched on CodeHawks just 2 minutes ago. So this competition is called Rock, Paper, Scissors, and this is like a playground for you to learn how to take part in competitive audits. So we launch First Flights every 2 weeks, and they are code bases that have hidden vulnerabilities in them. So if you've just finished Updraft or you've been through some sort of education in terms of blockchain security and you're wanting to take that step into the competitive audit landscape, then the First Flights are a brilliant place to start. These repos are often a lot more simplified. We're looking at around 200, 300 lines of code. This one is 349 lines of code, and they have vulnerabilities hidden in them. But so you can practice understanding different code bases, seeing how to create a submission on a competitive audit platform, and actually have your submissions judged by our judges at CodeHawks. So this is like a playground for you to practice, get familiar with the competitive audit space, how it works, how to take part. And once you've entered a couple of First Flights, you should be ready to then go into those real competitions and try and earn some dollars, which would be fantastic. So hopefully these will help. What we will do on this stream is we will go through the repo for this week's First Flights, and we will just talk through it, go through each function, say how it works, just to give you some familiarity with the code base so that you're ready to go in and hunt for those vulnerabilities that have been hidden in there. Now, let me share my screen quickly so you can see what we are looking at. If you want to check out the First Flights on the platform, all you need to do is go to codehawks.cypherin.io and click First Flights at the top here. And once you've clicked here, you can see all of the recent First Flights. Now, as I said, we launch these every 2 weeks. You may find it helpful to look through the previous First Flights as well and see the types of vulnerabilities that are being found during them. But this competition is launching, well, has launched today, 4 minutes ago, and it will be live for 1 week. So at midday UTC next Thursday is when the submissions period will end. So you've got a week to see what you can find and make those submissions. We will then go into a judging phase, just like a real competition, where our judges are going through the submissions, validating them and categorizing them. And then you will receive some feedback on your submission, whether it was validated and the severity score that that vulnerability got. So it does really mimic a real competition. But let's take a look at what this repo is anyway. So as I said, it's 349 lines of code. It's not huge, and it is based around the game Rock, Paper, Scissors. Marina says, is this a walkthrough? Yes, it is. So we're going to go through the scope, the format of what the contracts will be, and then we'll actually go through the contracts function by function, line by line, and talk through the intended functionality of the contract. We won't be talking through any vulnerabilities though, because that is your job over the next week. So let's take a look at what the description is for this repo. So Rock, Paper, Scissors DApp is a fully decentralized implementation of the classic Rock, Paper, Scissors game on Ethereum. The protocol allows players to compete in a fair and transparent manner with bets placed in ETH or using special winner tokens. So, about the project, Rock, Paper, Scissors DApp is a fully decentralized implementation. Key features here, so we've got the commit reveal mechanism ensuring fair play. We've got support for both Ethereum and token-based games. We've got multiple turn matches with best of end scoring. We've got automatic prize distribution and winner token rewards. And we have timeout protection against non-responsive players. So the smart contract system utilizes a commit reveal pattern to prevent front running and ensure players cannot see their opponent's move before committing their own. So there are quite a few functions within this contract that we will go through to make sure that the game is played fairly. Obviously, when we are making calls, often things can be very transparent, and we don't want them to be too transparent in this game, because in the classic game of Rock, Paper, Scissors, you say 3, 2, 1, go, and in this version, we can't exactly call at the same time. So we need to be able to commit our decision of whether we're choosing rock, paper, or scissors, and then we need to reveal that. So we will go through the contract in just a second, but let's take a look at this game flow. So player A will create a game with either ETH or the token as their bet for the game. We will then have player B join the game, and they will join with the matching bet. So however much ETH the first player has committed is however much ETH the second player should commit, or if they're just using the winner tokens created through this game, then they both need to just match that bet. Next, both players will commit a hashed move. So whether that's rock, paper, or scissors, they will commit their move. And once both have committed, then they will do their move reveals. So we'll see what move they committed, and we'll see who won. So the winner is determined for the current term, and then they repeat the game 3 to 5 times until all turns are complete, and the final winner receives their prize and winner token. So that's the game flow, but we will get to know this more when we're looking through the contracts themselves in just a second. In terms of timeouts, this is something that's really important for this type of protocol. If we start a game and one player is active and one player is not, we don't want to see the active players' funds just be locked up in the protocol. We want them to be able to have a time limit in place, and if the time does pass, then they should be able to claim back their bet, etc., etc. So making sure the timeouts are all in place is super important for a protocol like this. And we want to be able to, change the timeout period for the different parts of the game. That is controlled by the admin, but we will go through that in just a second. Finally, next, we're looking at the fees. Now, as the protocol owner, it would be great to earn some of the fees that are going through the protocol. You'll see this a lot. So 10% of protocol fees on all ETH games will go towards the protocol deployer. So actually, the protocol deployer reminds me that this repo has been very kindly contributed to us. Is it in the description who's contributed this? Chris, can you please remind me who contributed this repo? It actually was a community contribution, which is perfect. Lovely to see. Anyway, back to the description here. We've got 3 different actors within this protocol. We've got the players, so users who create or join games, commit and reveal moves, and participate in matches. We've got the admin, so the protocol administrator, who can update timeout parameters and withdraw accumulated fees. And then we've got the contract owner, initially the deployer of the contract, capable of setting a new admin. So the name of the contributor for this week is M3D. I don't know how they want me to pronounce that name. It is in the live chat though, so if you are watching, thank you so much for contributing this repo. If anybody else would like to contribute a repo, then do get in contact with us on Discord, and we could see your repo in the next first flights. Let's take a look at this repo though and see what's in store here with the contracts. Let's pull this up. So how we move on to actually reviewing the contracts here is we click on the view repo tab here, and this will take us to GitHub. You'll see here that we've got all of that information that we just discussed. We've got the scope for this audit. All of these things are super important to be reviewing. It's good to get in practice when you're reviewing the first flights, because these are really important things to look at when you're taking part in real competitions. You want to see what contracts are in scope, so you know where to look. In this case, we only have 2 contracts and they are both in scope. You can see the compatibilities here. So we can use ETH for betting, and we can use the rock, paper, scissors winner token, which is an internal ERC20 token. And you can see the setup instructions as well. So the instructions on how to build, how to test, and how to deploy there. And we have no known issues. Now, this is common within the first flight space, but it's not necessarily common within the competitive audit space. So it's a good habit to take a look at the full README, have a look at all these different pieces of information here, because the last thing you want to be doing is finding a vulnerability, creating a whole proof of concept, creating a submission, and then saying it's in the known issues. So we need to be getting in the habit of doing a full review of the README and all the details for a competition when we're doing this first flight, so that we don't forget later on when we are entering those competitions. Let's take a look at the contracts then. So we will go to the source folder and see what is in here. We've got 2 contracts in here. First of all, we have the winning token contract. So this is the internal ERC20 token. It is ownable, burnable, ERC20. It is called Rock, Paper, Scissors Winner Token. Its ticker is RPSW. It has inherited all the Open Zeppelin contracts. So it's just your standard ERC20. You can see here it's ownable, message sender here. There's no initial supply, and we can mint tokens here. So mint new tokens only capable by the owner, who is the deployer. So it's a standard contract. We don't need to go into that too deeply. You'll see this continuously across a lot of the first flight competitions and across a lot of real protocols as well, your ERC20 tokens. So let's move on to the rock, paper, scissors contract. Sorry, Bruna has just asked me to zoom in a little bit. Hopefully you can see this a little bit clearer now. Let's pull this. Can we get rid of this completely? There we go. So hopefully we can all see this a little bit clearer now. So this is the game contract. This is where all the fun stuff is. There may be something in the ERC20 contract. I'm not sure, but this is where the game is and all the fun stuff is. So let's take a look at this and talk through the contract line by line, so we're all familiar with the intended functionality here. First of all, we are going to import that ERC20 token that we created in the winning token contract. And we're going to get started with the rock, paper, scissors contract. So we've got some game moves outlined here. We've got none, so if nothing's committed. We've got rock, we've got paper, and we've got scissors. 3 words that I think I'll be saying a lot during this live stream. Next, we have the game state. So it can be created, committed, revealed, finished, and cancelled. So these are the different the game states that we'll have for this rock, paper, scissors game. Next, we're going on to the game structure. Now, there's a huge amount of variables in here. We've got addresses for both the players. Player A will be the creator of the game. Player B will be the second player to join. We then have the amount of ETH that has been bet for a game. Then we have all of our timings. So as we said earlier, deadlines and timelines are really important for a game like this, because if one player suddenly goes inactive, we don't want the other one to be left with their funds locked in a protocol. We need to have some sorts of timeout for each section of the game to ensure that that doesn't happen. So we'll have a timeout interval, so time allowed for the reveal phase. We'll have a deadline for revealing moves. We'll have a time, a event 256, which shows when the game was created. We'll have one to show the deadline for someone to join the game. Then we're moving on to the amount of turns that we have per game. So the total number of turns in the game and the current turn number. So what round we are on for this game so far. Next, we have the hashed moves. So commit A and commit B from player A and from player B. And then we have the revealed moves for each player. And we have the score for each player before we get to the current state of the game. So this is what we defined earlier up here. So it does look like a lot, but when you break it down, we're looking at the different players, the bets, the timeout features, and then we're looking at the different moves and the different stages of each move as well. So it's all pretty simple so far. Let's carry on through this. So we've got mapping of game ID to game data. So we're taking the game ID, we'll start at 0, 1, 2, 3, 4. It will be counted by our game counter variable here. And this will create a mapping to the game, which was outlined here. So if we have games 0, then we'll have all of this game information for the first game that's played with this contract. And as we go on, as the game IDs increase, they will all map to a version of this struct. Moving on to the next one here. So we have token for winners. So this is just initializing that winning token is immutable, public, all within there. Then we've got admin address for ownership functions. So the admin address variable. Then we have deposit amounts and timeouts. So this is where we are setting some variables that can be changed later on. So the minimum bet is being outlined as 0.01 Ether, and the join timeout is 24 hours. This is the time allowed for someone to join the game. If player A, myself, creates a game, I become player A, and then there's 24 hours for player B to join. Now, this is changeable, so the admin can actually change this, make it much shorter, make it much longer. I think it really depends on how many people are active when playing in the protocol. And the more activity there is, probably the shorter this can become. Next, we're looking at the protocol fee percent. So this is a constant variable here, and we have set that to 10%. So 10% of the Ether that goes through this contract will be preserved for the deployer and the owner, the admin. Accumulated fees here is just going to tot up like 10% of every ETH that goes through this protocol. This is going to keep a score on that, keep tabs on that, and tell us how much ETH has passed through, 10% of that, and how much the admin can claim from this contract later on. Carrying on, we've got a ton of events, pretty self-explanatory here. These are going to be emitted throughout the rest of the contract for when we create a game, for when a player is joined, a move is committed, and move is revealed, when the game round is over or the turn is over, when a game is finished, when it's cancelled. All of these events are pretty self-explanatory, and they've got a number of parameters in when they are emitted as well. But we'll go through the contracts and we'll see those events being emitted throughout. So we have the constructor here that is setting everything up. So we're initializing the winning token here, and we are setting the admin address, which was a variable outlined up here, to the deployer of the contract. This constructor, as we all should know, is a function that is called upon deployment. So the message sender is the deployer, and the admin address is being set to the message sender. Carrying on though with the next function here, we've got create game with ETH. We similarly have another function below called create game with token. As we discussed within the description for this protocol, you can play and place a bet with ETH, or you can play and place a bet with the token. Both of these functions are very, very similar. So we'll go through one, but the same applies for both. First of all, we are going to look at the create game with ETH. So we are going to set the variable for the total amount of turns. Like, are we doing best out of 3, or are we doing best out of 5? This is all determined here. Next, we have the timeout interval. So this is the interval for how long we should wait before somebody else joins the game. So starting off with some requirements here, we want to make sure that the player that has created the game with ETH has sent at least the minimum bet, otherwise the bet is too small. We are also going to require that the total number of turns is greater than 0, because we can't play best out of 0 games. There must be at least 1 turn or 1 round. We are also going to require that the total number of turns is an odd number. We don't want to be doing the best out of 2, because we might get to 1 all. So it needs to be an odd number. And finally, we are going to require that the timeout interval is bigger than 5, is more than 5, so at least 5 minutes here, just to give us enough time. That's a parameter that's been set by the deployer. Next, we are going to increase the game ID by 1 from this game counter. So our game ID is what creates that mapping from the game ID to the game, the struct with all of this data in about each game. So going back to our function here, we are going to create the game ID. We are going to increase the game counter by 1, and then we are going to set all of those parameters from the struct that we defined earlier. Bruna says, by the game struct, I could assume that a game can only have 2 players. Correct. That is correct. There can only be 2 players in this game. So what we're doing here is we are creating the game ID and then increasing the game counter by 1 so that we can make sure that each game has its own ID. And then we are going to define all of the variables with parameters within the game struct. So we've got the game ID, we've got player A, who is the caller of the create game with ETH function. We've got the game bet, which will be the value that the first player has set sent over to start the game. We've got the timeout interval. We've got the creation time, which is the current block timestamp. We've got the join deadline, which is the current block timestamp plus the amount of time they've got to join, the join timeout that was defined earlier. Then we have the total number of turns. We have the current turn, which is set to 1, and we have the game state. So the game state is currently set to created, and we can omit this event here. Going on to the next function, this is all the same again, but we are using the game token instead of ETH. The game bet is set as 0, but we have actually sent the winning token balance. Must have a winning token, which is required up here before we can create that game. So now that we've got a game created, whether that bet is in ETH or with tokens, we need to be able to have a function that the second player can join the game with. So we've got a join game with ETH function and we've got a join game with token function. Again, they are both very similar. We are going to first of all get the game ID parameter in there so we know what game people are trying to join. And then we are going to get the games and put the ID in there so we can see all of the information. And we are going to create some requirement functions. So we are going to require that the game state is in created. Otherwise, the game is not open to join. We are then going to make sure that player A isn't trying to play against themselves. You can't join your own game. Then we are going to make sure that the join deadline has not passed. So the current block timestamp is less than the game's deadline, join deadline. And finally, we are going to make sure that the person who has called this function has sent the correct amount of ETH, because the bet must match the creator's bet in order to play this game. Once those requirements have all passed, we will then set player B for the game struct with this game ID as the message sender of this function, and we will omit player joined with the game ID and the caller of this function. So we now have 2 players in our game, and the same happens for the join game with token function, but we have, look, we're checking that the player has sent a winning token and the same amount of winning tokens as the creator of the game instead of checking for the same amount of ETH. But those functions both are very similar. Moving on to the commit move. So we're going to commit a hashed move, and we are going to create put that as a parameter within our function. So we're going to have parameter 1, which is the game ID, and we're going to have parameter 2, which is the commit hash. This is an external function. What we are going to do as a player is we're going to say, here's our game ID, here's my commit hash, and then once they've both committed a move, then we'll reveal those and see who was the winner. So taking a look through this, we've got 2 required statements. We've got that the message sender is player A or is player B. They are a player in this game. And then we're going to require that the game state is created and it's not committed. Otherwise, we're not in the commit phase and we can't commit some moves. So the game current turn is 1, and the commit A is going to be empty and commit B is going to be empty. So this is the first turn and the first commits. This is to enter this block here. We are then going to require that the player's address is not 0. This would imply that the second player hasn't entered the game yet. So we are needing to wait for a second player to enter the game before we can continue. But if all of those parameters fit, then the game state is moved to committed. Otherwise, we are still waiting for a second player or for us to move within that commit phase. Or for us moves already committed for this turn, so we may be in a later stage as well. Next, once we've gone through that if else, we can move on to the next if else. So we are looking to see if the message sender is the first player, then we can check they've not already committed, and if they haven't, they can commit, and then same for the second player. Once they've committed, we will emit the move committed event. And if both players have committed, we'll set the reveal deadline. So if both of their commits aren't 0, bytes 32-0, then they've both committed, and game reveal deadline, we're going to set it as the timeout interval plus the current timestamp. So that function allows both players to commit their moves. Next, we are going to reveal our moves. So we're going to reveal the committed move, game ID of the parameters are the game ID, the player's moves, and the random salt used in the commit phase. So both players will put in the parameters, their salt, and this will allow us to reveal their initial commit. So you can see this all here. We will encode packed it, ABI encode packed it, and go backwards and check that the commit is equal to the move and the salt. And once that has been confirmed, we will then be able to see the winner of the game. So we'll check that when they're revealing their commit, whether they've rocked, papered, or scissored. And then once they've got their decision, we'll be able to see who the winner was for that game. So the moves will be revealed and we will determine the winner. If we have some timeouts, then we need to check them here. So claim win if opponent doesn't reveal in time. So both players can commit a move, but they both need to reveal their moves. Otherwise, we need to time this out because, as I said, one player will have their funds locked in to the protocol. So this is what that function is for here. I am going to speed this up slightly because I know we're going over time. But the next couple of functions are for timeouts. As I said, we don't want somebody having their funds locked within the protocol. So if one player isn't moving fast enough, we need to have some time constraints in there. And if they are moving too slow, then we need to allow the other player to withdraw their funds. Finally, next we have a cancel game function, and this is for a refund if the game is still in the created state. This is something that should be allowed if we don't have two players taking part. Next, we have the timeout join function. So cancel the game if the join timeout has passed and no one has joined. We need to set the join timeout length though. So set the join timeout period. So this is the period that needs to pass in order for us to say, okay, actually, nobody else is going to join. Let's give them their funds back. Next, can timeout join, check if a game is eligible. This is just a view function. So can I still join this game? Am I still within the time limit? You can call this function to check for the specific game ID. Moving on to the next couple of functions very, very quickly because we need to wrap this up. We've got the owner as a view function. We've got the token owner as a view function. Lots of view functions down here. We've got the set admin function. So this can only be called by the admin address. So the admin can transfer ownership and admin responsibilities onto another address if they choose to. And the admin should be able to withdraw any fees that's been accrued during people using the protocol through the withdraw fees function here as well. Finally, we have the determine winner functions. We've got a couple more functions actually. We've got the determine winner function. So this is going to take the game ID, and this is an internal function that some of our earlier functions call upon for us to determine the winner. So to go through who played rock, who played paper, who played scissors, who the winner is, and through all of these if-else functionality, we will determine the winner, and then we will count up the winners for each round and see who the actual winner is for the entire game, and then call the finish game function, which again is an internal function. This is used to finish a game, close everything up, wrap everything up, and send the winner their winning funds, their winnings. Finally, this is the last function, I think. We've got the handle tie. So we'll look at the game ID, and if the players have both got the same score, then they will receive their initial bets back. And we have a cancel game and refund function. So refund ETH to players, refund token to players. I'm sorry that we've rushed through the ends of this, but this is quite a long contract, and I hope that you've been able to catch the gist there. The initial part is really important in terms of players are going to we're going to define that game struct, and then that's just going to get changed throughout every stage of the process in terms of the game. The timeouts are really, really important. So it's really a good idea to take a close look at those, and just to look at how the game struct changes throughout the game is a good idea as well. But if you have any questions about this repo, do let us know. Do head over to our Discord. The link is in today's description. Equius and some other members of the team are active in there to answer any of your questions. And thank you so much to the contributor of today's repo as well. But that is all we have time for today. So thank you very much for watching, and we will be back here in 2 weeks. So I will see you all then. Goodbye.